Hello everyone. In this talk, I'll be talking about our new paper on fine-tuned deep features for unsupervised domain adaptation. This is a joint work by Dr. Wang from Department of Computer Science at Durham University and Professor Meng from Alliance Manchester Business School, the University of Manchester, and also Professor Toby Breckon, also from Durham University. First of all, what is domain adaptation? Let me explain the concept of domain adaptation by giving an example. Suppose our goal is to classify different breeds of dogs in sketch images. Then the domain of sketch images is our target domain. Usually, we don't have enough label data in the target domain for training the model in a supervised learning way. To solve this problem, we can utilize the label data in a different domain, such as natural image domain, which is the source domain. The source domain and target domain share the same set of classes, but also have a data distribution shift. Existing approaches to unsupervised domain adaptation can be categorized into two groups: end-to-end learning approaches and feature transformation approaches. In existing works, both groups of approaches take advantage of pre-trained models on large image datasets, such as ImageNet or other even larger datasets. End-to-end learning approaches use the pre-trained networks as backbones and modify the network architectures to learn domain-invariant representations and classification heads. In contrast, feature transformation approaches use a pre-trained model as a feature extractor and extract the deep features for the subsequent transformation and classifier training. It is obvious that feature transformation approaches rely on the capabilities of pre-trained deep features. One obvious question is, can we take advantage of both types of approaches and further improve the UDA performance? To answer this question, we designed the pipeline consisting of two stages. In the first stage, we fine-tuned the backbone network on dataset from the specific domain adaptation task so that it can be used to extract improved features for the specific domain adaptation task. Once the improved features are extracted, in the second stage, we use an enabling feature transformation UDA approach to do the target data classification and get the final results. In the baseline method, the data from specific domain adaptation tasks are not used for training the feature extractor. We believe this is one of the limitations of the current feature transformation UDA approaches. As a result, we investigate the use of source and target domain data in two experiment settings. Firstly, we use source data only during fine-tuning the backbone models. Since the source data are labeled, it is straightforward to use them for fine-tuning. Secondly, we make use of both the source and target data during our model fine-tuning. Since the target data are not labeled, we need to use pseudo-labels, which have been an extensively explored technique in UDA approaches. We find that fine-tuning the backbone network in a conventional way may not be optimal. Instead, we apply a strategy of linear probing followed by fine-tuning and get better results than directly fine-tuning. One key in our model fine-tuning is that we treat the batch normalization layers in a spatial way. Specifically, we only update the affine parameters gamma and beta, while the mean and standard deviation are fixed as what they are in the pre-trained model. We find that this trick is important for domain adaptation, as demonstrated in prior works. In the second stage of our pipeline, we employ one typical feature transformation UDA approach, namely selective pseudo-labeling. This approach uses LPP to learn a common subspace in which both source and target data are well aligned. To learn a better subspace using LPP, the unlabeled target data are selectively pseudo-labeled so that they can contribute to the learning as if they are labeled data. The subspace learning and pseudo-labeling are iterated for a certain number of steps, and the final target data classification can be done in the learned subspace. We conduct experiments on the commonly used benchmark dataset for domain adaptation Office 31, which consists of 31 classes in 3 domains. In the slide, on the left side of this slide, we show some exemplar images from 3 domains. We use 4 different backbones in our experiments. Results in the table show that our proposed approach can achieve the best accuracy regardless of the backbone models, particularly when the typical ResNet 50 backbone was used. Our chosen feature transformation approach, SPL, can achieve an average accuracy of 90.1% over 6 domain adaptation tasks. When using the pre-trained ImageNet pre-trainer model as a feature extractor, SPL gives an average accuracy of 89.6%. And in this group, our proposed method achieves the highest average accuracy when compared with state-of-the-art UDA approaches. Other than the CNN-based backbone, we also investigate DataSmall and DataBase, which are vision transformer-based models. And recently, we can see some literature using these vision transformer-based models as their backbones for UDA methods. For example, CityTrans and SHORTS and CGDM. Compared with these vision transformer-based models, our proposed pipeline can also achieve better results. And overall, our proposed method using a database as the backbone can achieve the highest overall or average accuracy on this dataset. More challenging dataset, Office Home, which consists of 65 classes in 4 domains. As shown in the table, when using ResNet 50 as the backbone, on Office Home dataset, the fine-tuned deep features lift the accuracy of LPL from 71% to 71.8%. In addition, when other 3 backbones are used, our proposed approach can always achieve the best performance comparing with state-of-the-art UDA approaches. Based on the experimental results, we can conclude that the proposed method is effective for unsupervised domain adaptation, and we can achieve state-of-the-art performance on two commonly used benchmark datasets. And different components in the proposed approach make their contributions to the superior performance. Features learned by deep models can be further enhanced by feature transformation approaches such as SPL for unsupervised domain adaptation. As a result, we can always combine two types of approaches so that we can get better accuracy. And lastly, even better UDA performance can be expected if we can use more advanced deep features. And these deep features can be either from more advanced pre-trained model or some specific deep learning models designed for UDA problems. Thank you very much for listening. That is all for this talk. And if you have any questions or comments on this paper, you can contact me via this email address. Thank you again. Have a nice day.